Hi, my name is Miranda.
My name is Ronghe.
My name is Leon.
My name is Jonathan.
My name is Selena.
And we are
Miracle
STEM
STEM
Engineers. And this is our final presentation.
So this is the final presentation for Miracle STEM Engineers. As for the table of contents, we'll go over the final system overview, operations, mission demonstration, results and next steps, scaling to a flight spacecraft, orbit, power budget, mass budget, and lesson learned. Our mission is to design and develop a CubeSat capable of efficiently patrolling wildfire-prone regions and detecting ongoing fires through real-time image capture and analysis. So our operation time frame is 1 year, and our daily patrol area is approximately 25,000 kilometers squared, and our image capture and analysis rate is 1 operation per minute, and our objective is to detect active wildfires using advanced imaging techniques and notify the fire department for rapid response.
This is a bit about how all of this will work. So first, our CubeSat will continuously monitor wildfire-prone areas and capture images to prevent damage. And if we do detect a wildfire, the CubeSat will send precise coordinates to our ground station, who can forward it to firefighting agencies. And finally, we can gather data that will help analyze wildfire patterns and improve forecasting in case these events do happen.
Wildfires can be really impactful. They can harm wildlife, destroy ecosystems, and pollute the air, which causes global warming. They can really be life-threatening since the smoke can cause lung diseases and the fires can move really fast. There are also economic and social impacts because the fires can be really destructive, making it really costly to recover from.
More about our CubeSat is the software component. So our sensors will be used to detect the nearby environment, navigate our CubeSat and monitor its condition. And the code is used for fire detection, where you use imaging techniques to look at the fire. And the communication is used for the communication between the ground station and the CubeSat.
Here's a bit about our CubeSat's hardware. So for non-electronics, we have standoffs, plates, baseplate, corner piece plastic bar with a square or round holes, 3x3 plate, and a center hole. And for electronics, we have an IMU, or inertial measurement unit. We have our Raspberry Pi 4B, solar panel, and finally a battery pack. Now we'll present our CubeSat prototype operations video, which includes the CubeSat starting up and also a demonstration of our mission. And now we'll present to you the ground station operations video, which include the command prompt operations used during the CubeSat operation.
For our mission demonstration, we used 3 different maps to test the fire detecting ability of our CubeSat. As for the last test, we simulated a wildfire simulation with the green paper being the forest and smaller red pieces being the wildfire. and over time we will keep adding red pieces to make the wildfire spread. And then we hover over our CubeSat to make sure that it detects the wildfire over time. Here are our results and next steps. So through our data collection, we have generated 4 different graphs. The first 2 are shown here. So for map 2 graph, we can see that the values are higher, and that makes sense because for our second map, we have the most amount of fire shown on the picture. So that's why a lot of fire is detected with a greater area. As for our third graph, we can see that it has the lowest values because red is not really present on the map, and the only present colors are orange and yellow, and it also has a smaller fire area. That's why we have lower fire area being detected. And lastly, for our simulation, we can see a linear representation, and that happens because throughout the simulation, we kept adding more fire pieces to simulate the wildfire spreading, and that's why we can see that the wildfire is shown as increasing over time. For our error analysis, we can see that fire detection is fairly accurate, but fire area calculation is not. So throughout our coding process, we found out that our area calculation either gives a result that is too big or too small. So we can fix that by changing the calculation techniques so that we can make the fire area calculation more accurate. Another problem we encountered is that the data is not collected in 1-minute time increments. So when we look back at the graph, we can see that the time is represented in decimals, but not integers. So we can make improvements using the Python time function. We can adjust that so that the time is incremented correctly when we collect the data.
This is how we plan to scale our CubeSat to a flight spacecraft. Our model represents real regions prone to wildfire at a smaller scale. For the first map, 1 square inch corresponds to 2 square miles. For the second map, 1 square inch corresponds to 0.08 square miles. For the third map, 1 square inch corresponds to 0.6 square miles. The mass of our CubeSat would increase from 0.87 kilograms to 10.5 kilograms, considering a 12U satellite. Some additional components needed for the CubeSat would be: the surface area of the solar panels would have to increase to match the increased power requirements of the larger satellite. A system would have to be created to ensure the satellite camera would always face the Earth. A GPS system would be installed for satellite tracking. Thrusters would have to be added to ensure the satellite stays in an optimal orbit. Heat dissipation materials would have to be added to account for the larger amount of heat generated by the larger satellite. And support structures would have to be added to support the antennas and solar panels. This is our first map, this is our second map, and this is our third map.
For the orbit of our CubeSat, it will be in low Earth orbit at 200 kilometers to 300 kilometers altitude, and it will circle around the equator at 2 orbits every 24 hours, day and night.
Here's our power budget. Firstly, what we have on the left is a table of values for when the solar panel was rotating parallel to the sun along with its graph. What we did was that we stopped at every 30 degrees we rotated parallel to the sun and recorded what data we had on the adapter, which is why we have from -90 to +90 degrees in the first row and the voltage, current, energy, and power beneath it. And a little different to the previous one. Here what we have is the table of values for when the solar panel was rotating perpendicular to the sun and its line graph. For -90 and -60 degrees, it wasn't facing the sun at all, so no sun energy was absorbed, which is why there's no data shown on the adapter for these 2 angles. All of the data for these 2 tables were directly transferred over from the adapter screen. Next is the power consumption and generation for the 2 modes we have, nominal and active. This table basically just shows how much power they used and how much the battery can support. As expected and shown, more power is used during active mode since that's when the CubeSat is missioned to work more and take photos. And lastly, this table shows the battery life for both modes, assuming that the conversion efficiency is around 90%.
Here's the mass budget of our CubeSat. The tables have each component's material, cost, manufacturer, and mass. While building our CubeSat, we used various materials including PCB, acrylic, aluminum, nylon, and zinc. We weighed out each component along with contingency numbers to account for errors during manufacturing and the weighing process. The total mass of our satellite was 610.43 grams with contingency and costed $202.75.
Throughout this project, we faced a lot of unexpected challenges, and here are some of the biggest lessons that we learned. So first, we learned to not underestimate how much time it would take to learn technical skills. For us, designing and integrating everything, especially in CAD modeling and software design, took far more time than we expected. Next, we also learned the importance of defining our mission objectives early and clearly. At first, we had big ideas, but we had to narrow them down to avoid scope creep in the end. We also had to watch out for real-world constraints, which included weather, power, and communication limitations, because this sometimes resulted in our testing being delayed. But despite these challenges, our CubeSat will make a real impact, which includes helping disaster management teams anticipate and respond to wildfires more effectively.
Thank you so much for listening to our presentation. It was really rewarding to be working with these CubeSats as a team, and we learned a lot from it.